So we're going to talk now about the concept of relative dating. Whereas in the previous video, we talked about absolute dating. Relative dating is what you do when, one, you don't have a mass spectrometer. Two, there's nothing in that outcrop that you can determine it has radioisotopes in it that are easily ascertained. Or you're just looking at a rock outcrop, trying to figure out what happened first. So, relative dating involves approximately 8 different laws that help you ascertain which rock unit in a larger formation occurred first. And which ones occurred later. So we're going to go through each of these 8 ones, and a rock outcrop can be as small as a hand sample with a couple little interesting features in it. A rock outcrop can be many, many miles across and many thousands of feet thick. Now, what's cool is if you join us on any of the field exercises this semester, or you do any of the online field assignments, which, by the way, everybody here, I'm hoping you do one of those. It's kind of important for your grade to do at least one of the field exercises. You'll be in contact with some of these laws of relative dating and get a chance to practice them. And this is useful far beyond geology. This is great if you want to be a detective, if you just want to sort of figure out who made the mess. It's a lot of fun things to be done once you start to understand these. I feel kind of happy recording this from my house because my house is a hot mess, and you might even have a couple test questions that have photographs of piles of crap in my house. So first rule of relative dating, it's a bedding, it's a plane, it's superposition. Can't you tell I'm dressed as a super by the outlandish getup? No, that's because I'm doing something else interesting tonight, but superposition is a very simple rule that says the youngest formation is usually the formation that is on top. Now, there's only going to be 1 or 2 times when this is not the case. One, if you have a lava flow that somehow goes between 2 layers. Sometimes you get something known as a sill, which is a horizontal lava flow that will sort of find its way between a layer of rock that's more dense than it and a layer of rock that's less dense than it. It's often the contact between 2 different sedimentary units. There are some cracks that if there's a magma trying to make its way up, it'll go horizontally along them. Or in other cases, when the rock unit layers are upside down. Great example of this from my field of glaciology was in the late 90s. They did a large drill core on the surface of Greenland, sunk that drill core down into the Greenland ice, nearly all the way to the bed. And in Greenland, you can see really nice, easily counted layers that pretty much, at least for the upper part of the core, correspond to annual layers. And by looking at the chemistry of those layers, you can determine quite a bit what kind of climate the world had at that time, at least little hints of temperature and things like that. And so what they found evidence for in this drill core was an event at the beginning of the last ice age where the climate went from something very similar to what we witness in the present day to a climate that was very much deep ice age climate, a drop of 10 degrees Celsius in a matter of a few decades. They called this Event 1. And they were trying to figure out what might have caused it, why it was what it was, and whether we might have something like that in our future. Now, you may wonder, wait a minute, why don't we hear about Event 1? The reason we do not hear about Event 1 is because they found out that the layers in the bottom part of the core had been overturned as the overlying ice had flowed over and kind of just sort of caused that lower bit of the ice to shear, eventually rotating, meaning that the layers towards the bottom were no longer out in proper order. This is what gets into our nice little segue into our second law. The second law is the law of original horizontality. Pretty much, we always assume in a sedimentary deposit, especially on one that's sort of like, reasonably small scale, like hundreds of meters, or even a kilometer or two, that sedimentary vents tend to be laid down as horizontal deposits most of the time. And so do you see any sort of tilting to the sort of like larger scale layering of that? That tilting event clearly happened after the sediments were laid down. Likewise, this is also what you're going to see if you see any folding. So you get the screen to work with. That's better. Yes. Likewise, if you see any folding, these folds are going to be corresponding to layers that are older. Those folds are going to happen after these sediments are laid down. And so if you join us out in the field, hopefully we get to see a couple of folds. We'll be talking about this in class on the 28th, so stay tuned. More fun to come. Finally, the final one on this page this is actually one of the most important ones, is cross-cutting relationships. You can see this just about anywhere you go. You don't have to be looking at a classical outcrop to observe this. If a feature cuts across a layer, this could be a fault, this could be a crack, this could be joints, or as we call them in geology, dikes. These are vertical sheets of lava. Anything that cuts across is going to be younger than what it cuts across. So you see a crack in the sidewalk? It's younger than the sidewalk. Sometimes I've seen places where there is a crack in the street, and then there's a speed bump, and the speed bump is not cracked, indicating that they put the speed bump in after the street cracked. But after the street cracked, and that, of course, the crack happened after the street was laid down. And so you can sort of see this little sequence of events. What's really cool also, and one of the things I try to hint at when I'm really on my ball, is that human activities are not really anything new on this planet. We're just taking everything that geology has done for millions of years and changing the speed at which a couple of those processes take place. So the third rule here is the rule of, the fifth rule here is intrusions. If you see an intrusive body, it's going to be younger than everything that's coming up. And we'll see this really vividly on the March 1st when we climb Calaveras Hill and we see a lava flow that's clearly come up through a bunch of other stuff. Now, one of the things you want to look for around an intrusion, a lava flow, or one of those bodies, is generally when it's coming up through stuff, just like we saw on Friday's lecture on the 14th, we saw the contact metamorphism. Generally, you'll see whatever rock that lava flow has been in contact with, whether it be a lava flow, whether it be an intrusive body, that's the stuff immediately in contact with it is often cooked. Now, not always. It's not always hot enough. It's not always hot enough long enough. Sometimes it's not made of minerals that really reveal how hot they got very easily. Generally, an intrusive body will be younger than what it is cutting through. Likewise, inclusions. You may have heard the story of a how they found a human tool embedded in some rock, and that rock had been dated to be many, many, many millions of years old. And everyone's like, well, this is proof that evolution's wrong. No. See, it turned out the age they got, the pieces of the rock they used to get that age were actually, and the human tool were both inclusions in the same rock formation that had formed much more recently. So, if you see a bunch of cobbles all cemented together in a sandstone, in a conglomerate, the cobbles that make up that conglomerate probably originally formed long before they ever became part of that conglomerate. All right, and probably also had quite a bit of a transport history. In fact, often what you see is sometimes on at the top of erosion surface, right above the erosion surface, is you'll see little pieces of the outcrop below that was clearly eroded nearby. We'll see this very vividly when we do the Tourmaline beach trip on the 7th of March. So fifth law here, or let's see, now we're down to 7. Geez. Law of unconformities. This is probably one of the most important laws of the bunch. In fact, I'm saving this one for last because it really is. This is the one that probably next time I do this video, we are going to have a black whiteboard with some diagrams of what the heck's happening here. So this looks a little bit confusing here, but imagine you get a sequence of rocks all being deposited on top of each other. Eventually, and generally, as long as your sediment is in an area that's underwater and subsiding, more sediment can be laid on top of it. This is, for example, how we got these packets of sediment thousands and thousands of feet thick that were first used to sort of infer that there were large-scale processes reshaping this planet before we finally start to understand a little bit about how plate tectonics works. However, when you take a packet of any material and move it upwards, eventually it's subject to erosion. And as it erodes, all that material that was preserving all sorts of records gets lost. So if you ever want the quick definition for an unconformity, short answer is it's an erosion surface. Now exactly what that erosion surface looks like, this is a fairly dramatic example where we have rock that was uplifted, or that was deposited, hardened, tilted, uplifted, and then eroded flat. So this erosion surface right here. Now it's fully possible to have unconformities that are almost exactly parallel with the layering not only above them, but also below them. We call those paraconformities. Now, whenever you see one of these, what it's telling you is simply that erosion happened. So, one great way, so another thing you might look for at an unconformity is evidence for the formation of a soil. You do not see these at every unconformity, but you see them often enough that they can be a useful indicator of an unconformity, because sometimes it can be very difficult to distinguish a lava flow cutting under stuff versus a erosion surface over it. Turns out sandstone both sandstone and heavily weathered granite both contain quartz, and clays and feldspar because the feldspar is starting to weather into clay. And so one really shining indicator that helps you distinguish between the two is, look for the soil contact. If you see some kind of soil horizon, that's a very strong sign that you're looking at unconformity. Whereas if you're looking at an intrusive body, you're probably looking, and you'll probably see a little bit of metamorphism around it. That'll help you determine it. Because often intrusive bodies, the tops of them are flat enough that it's hard to distinguish that. So if you have an intrusive igneous body below and a sedimentary layer above, look for either a soil to tell you that it's an unconformity, or look for contact metamorphism to tell you that it is an intrusion. Then the final one is lateral continuity. This is one we don't really do enough of in this class, but it's going to be important. But it gets really important if you start doing oil or other sorts of economic geology issues. That rock layers extend for some distance over the surface from a few meters to hundreds of kilometers, depending on the conditions during deposition. So when we did sedimentary rocks, I mentioned that in any one location, any one time, you're going to have all sorts of different types of sediments being deposited. Sometimes one's very different. So often people, when they see like a very long sedimentary layer, like you get east of the Rockies, there's certain sedimentary units that extend for hundreds of miles. They think that that sedimentary unit was deposited all at the same time, when in fact, you're probably looking at is the rising and falling of a sea. And that's the deposition you're actually looking at. All right, that concludes our